The next thing that we talk about is a prism. I told you a prism is being used, or rather 2 prisms are being, I think it's 4. The prisms are being used here, okay, to invert the image. Okay. First, let's say like how this works. And I want you to pay attention to this because there are many questions which are asked about this in your exam. So it is important that you pay attention here. Okay, let me take a prism. Let me take a triangular prism. Okay. So this is a prism. Let's say, this is clearly 90 degrees. Let's say this is 45 degrees. 45 degrees and 45 degrees. Okay. So this is glass, clearly, yes, this is glass. Let's say the refractive index is 1.5. Mu of the glass is, see, mu G is equal to 1.5 roughly. So here outside the glass is air. There are 2 mediums. One is glass, we have prism here, and then outside it is air. So this is one medium, and another medium. This is medium 1, and this is medium 2, and outside here again medium 1. So air, glass, and then air. It's typical setup, right? Okay. It's like this. It's like my spectacles. Air, then glass, then air. It's that kind of thing. So then I have a prism, a thick prism there. Let's see what will happen now. What I'm going to do is I'm going to send a ray which is parallel to the normal of the surface. Let's say we take a normal, any normal at any point, let's say. It's going to be like this, right? This is normal. For this surface. Notice this is an interface, right? Air, glass interface. This is also an interface. Glass, air interface. This is also an interface. Glass, air interface. Okay? All these 3 things are interfaces. This one, this one, this one. Inside you have medium. Outside you have medium. These are interfaces. You know, the sides of the triangle. Okay, now let me send a ray like that. So what is going to happen? Will there be any refraction? Will there be any deviation in the path? No. Why? Because you are sending the ray through the normal. If it is perpendicular to the surface, no refraction in the sense, no angle, and no deviation in the ray will take place. So it will go straight. That's what we saw. I is 0 or will also be 0. It goes straight. This ray will go straight. Okay? So it goes here. But then there is a problem here. That's a problem. This is an interface area, right? Inside, fine, glass. Now you have an interface here. Glass, air interface. This is also air glass interface, but then you hit the interface at 90 degrees. Okay? The normal the ray is 0. So you hit it perpendicularly, then you go straight without any deviation. But here you see the normal is here. This is the normal. And then this interface is hit with an angle. I. Now the question is, what will happen to the ray? Will it refract or will it reflect back? That's the question. And that depends on the angle of incidence, and that also depends on the refractive index. Well, so what is this angle going to be? This angle is 45 degrees. Correct? This must be 45. This is, look at this. This is 45, this is 90, which means that this must be 45, and if this is 45, this must be 45 too. So this must be 45 degrees. So I am hit this, the angle between the normal to this surface, this interface, is the normal to the interface, and the incident ray is 45 degrees. And what should happen? Again, that depends on the refractive index. Is this a critical angle? If the critical angle is less than 45 degrees, what is happening here? Suppose for this glass 1.5. What is the critical angle? Critical angle for that is, if you have 1.52, then critical angle is 41.14. So IC for this is 41 degrees roughly. Okay? But you are hitting it at an angle of 45 degrees. So what will happen now? This ray will not go to the other medium. It won't get refracted. There will be a total internal reflection. Why? Because the I is now greater than 41 degrees. And that is this is decided by the refractive index. For example, instead of a glass prism, if it had an ice prism made of water, then what would have happened? The same shape, everything is same. Instead of glass, I had ice. Then what would have happened? Well, for ice, for water, the critical angle is 48.75. I hope it holds good for ice too. So it's 48.75. But now I am hitting only at 45 degrees. So if it was an ice prism, then I have not made an angle which is greater than the critical angle for ice. So I will refract. The light will go out. But this is a glass prism. For glass prism, the critical angle is 41 degrees, and I am hitting it at an angle of 45 degrees. So there will be total internal reflection. Light will not get out. Okay? So when light doesn't get out, then what is it going to do now? So now there will be reflection. So the moment there is reflection, I must be equal to R. So if I is 45 degrees, then your R, the reflected angle, must also be 45 degrees. So this will come like this. Let's see. Okay. I've jumped the gun, but let's see. So now the ray will come here. Now there is another interface. This interface between glass and air. Now what happens? But then this ray is going through the normal. If it goes through the normal, then it will go into the other medium without any change in its path. So it will just go through like that. Suppose we had made an angle, some angle here, then clearly then you need to make a normal here. Then you need to see whether you have crossed the critical angle. If you have crossed the critical angle, gone past the critical angle, gone above the critical angle, then this will reflect back into it. Otherwise, then it will refract using sin R. So in this case, because this is 45 degrees, you got 45 degree angle here, then it will come like that. If this was not 45 degrees, then you can have a different slope, for example. Okay, instead of the slope, you may have a slope which is different. Okay, then you have to draw normal to that, and then you see what your angle is, and you see how it's going to be affected, and how this interface is going to behave. So for each interface, you have to do this. And again, if this was a prism made of ice, water, then this would still have gone past it. Okay? This would have gone something like this. You are going from denser to rarer, so denser to rarer, and clearly then light would have gone like that. If this was ice, if this prism had been made of ice, then light would have come out. It is made of glass with a refractive index 1.5, which means that the critical angle is 41 degrees, but then when you hit this interface, you have crossed the critical angle, your angle is more than the critical angle, so there will be total internal reflection, and then you need to see what will happen to this. You don't have to worry about total internal reflection when you go from rarer medium to denser medium. But once inside the denser medium, and when you try to come out into a rarer medium, then you have to be careful. So you have to see whether total internal reflection will take place or not. So this is how this works. And if you understand this, then it is very easy for you to invert images. We'll see. Now let's see a simple case. I have a prism like this, a glass prism. This is 90, this is 45 degrees, and this is also 45 degrees. Okay, I have an object. This is A of that, and that's B of that object. Okay. Now let's see what will happen to a ray that goes straight, normal to this. So this will be normal, and it will go hit this, and I told you that this angle is also 45 degrees, because it is 45 degrees, and then this will be 90 degree reflection, and that is perpendicular to this interface, normal, and this ray will be in parallel on the same line, so they will just come out like that. Okay, this is one. And then if you do the same, but this is going to be my A dash. As you see from here, it will look like A is here. Okay, you will see that you won't see A to be here. When you look at A from this point, it will look like A is here. But that's where the ray seems to come from. Now B again is also a straight line. So rarer to denser, so you don't have to worry about total internal reflection. So it will keep going straight. This is also parallel to the normal. Go here and get here. This is also 90 degrees, 45 degrees and 90 degrees, and something like this. So this will be your B dash, and this will look like, this is your B. This is how it will look like, okay, as you see from here. Okay, so how can I use this to invert the image? It's very easy. I'm going to take the same prism, but I'm going to have it like this. Okay. So this is 90 degrees now. So this is 45 degrees. This is 45 degrees. Okay. So how is it going to happen? Okay. Now this is my A, this is my B, let's say. So this is my A, this is my B. So this goes straight as usual. So this interface 90 degrees, so normal, so it will go straight. Okay. But once it goes there, clearly you can see that there is an angle of 45 degrees, it makes it the normal of this interface. So then you get here. Okay. So again, when it comes here, it makes an angle of 45 degrees to the normal, and if the refractive index is good enough, it's 1.5 or something, then you'll have total internal reflection. So you get this. This is my A dash. Let me talk about B. So this goes straight as usual. Okay, normal, so it will go through it straight. And then here also, this is 90 degrees. So this will get reflected, total internal reflection, because you are exceeding the angle, critical angle. So now this will go straight. B dash. See, AB is now B dash A dash. You can see that the image is inverted. And a technique like this is what is used in this. So when you use two lenses to get an image, like a telescope, and clearly the image is going to be inverted. But now, if you use a prism, then I can invert that image and then make it erect here. If it was BEA, then you will get this. Same thing. Okay? So I can invert it. If I can use a prism to invert the image, then I can take an inverted image, use the prism to invert it to get the erect image. Okay? So that is what binoculars use. So that is why you see you have this lens here and then your eyepiece is here. It's not exactly the same line. Okay? You can see that. The eyepiece is here and then your objective is here. Usually the telescope, they are along the same line, literally. Refractive telescopes, if you see, the most part. So which means that like there is some kind of a deflection that is taking place inside and then reverting it and then giving it to you. So it happens on both sides. So this is what is happening. Okay. And another arrangement could be something like this. Prism like this. Okay. So I can have A and have B. Okay. So now clearly this would go hit this, but then now normal is like that. But then like you are going from rarer medium, denser medium, so you don't have to worry about internal reflection. That will just be a refraction. So and it will, the ray will bend towards the normal. It is going from rarer to denser. Something like this. Okay. But now when it comes to this interface, this medium and this medium, when it comes to that interface, if you cross the critical angle, then you will go like this, right? Okay. So now if you go like that, then clearly here again go like this. Okay. So now this is for, but what will happen to this? Right here. Okay. Now this will hit like this, and then this will go like this, and this will go like this. So the total internal reflection will happen here. Won't allow the light to go out because you would have exceeded the critical angle here. So that's how it depends on the material and stuff. Okay. So you choose the right material so that for this angle you get total internal reflection. So you get that now. So now if you have A and if you have B, this is A dash is here, then B here. You see now I've inverted it. So there are ways in which you can do this.
The ability of a fiber optic strand to transmit data is based on the optical phenomena of total internal reflection. Light waves have three primary properties that affect total internal reflection. These are reflection, refraction, and refractive index. Here we see a light wave as it propagates straight through two different mediums. The speed of the light wave changes depending on the medium through which it passes. Medium A and medium B each have a different refractive index, designated by a lowercase n. Medium B, with the slower moving light wave, has a higher refractive index than medium A. For example, water has a higher refractive index than air. A wave propagating through water will travel at a slower speed than the same wave in air. The boundary or interface between two mediums is where the refraction and reflection occur. Refraction is the bending of the light wave as it passes from one medium to the next. If the second medium prevents light from passing through the interface, reflection occurs. Two factors must be considered when determining the degree of refraction or reflection: the angle at which the light wave strikes the interface and the refractive index of one medium in relation to the other. Snell's law is used to determine the amount of refraction that will occur between two mediums. Imagine a line perpendicular to the interface. This line is referred to as the normal. A light wave traveling straight into the new medium or along the normal will change speed but not change direction. However, when the light hits the interface at an angle, the change in light speed will cause the beam to change direction slightly and propagate through the second medium at a different angle. The angle at which the light hits the interface is referred to as the angle of incidence. The angle at which the light propagates through the new medium is called the angle of refraction. By placing the known values into Snell's formula, the degree of refraction can be determined. Snell's law states that if the refractive index of the second medium is greater than that of the first, the angle of refraction is smaller than the angle of incidence. Conversely, if the refractive index of the second medium is smaller than that of the first, the angle of refraction is greater than the angle of incidence. This is the principle that enables light to travel through a fiber optic strand. The core has a higher refractive index than the surrounding cladding. A light wave from the core will increase in speed when it enters the cladding, which has a lower refractive index. Notice that as the angle of incidence becomes greater, the angle of refraction approaches the boundary or interface. If the angle of incidence is such that the refracted light wave travels along the boundary between the core and the cladding, it is known as the critical angle. If the striking angle or angle of incidence is greater than the critical angle, the light will be reflected with no refraction. This is what is known as total internal reflection.
Total internal reflection is important in technology. A lot of communications are done, including telephone and other communications. You may have an optical cable in your home stereo or home theater system that communicates audio information through an optical cable. The principle is total internal reflection. If we come in at a glancing angle, then all of the light that's incident on this surface and on this surface will be reflected back internally into the material. So it works for glancing angles, and the beam needs to be confined within a material that is more optically dense, has a higher index of refraction than the surrounding material. But any shape will do. You can use a rectangular shape here, you can use a circular shape, confining all that light inside of that fiber. This is a more typical light optical cable or light fiber. I'm just going to introduce the beam here. You'll see it come out on the far end. This is an example of, we have a source of light in the base here, and each of these, all they are strands of plastic, and they are channeling the light through them. And they can be bent or whatever, and they'll still channel that light. There is a certain radius. If you bend it, if you kink it really hard, then that brings you away from the total internal reflection, and you lose the effect. But very effective, very important in today's technology, total internal reflection.